This lesson will cover solving equations involving hyperbolic functions, either by using the identities or the exponential definitions. Recall the following identities. So Shinex can be written in exponential form, as can Coshx and Thanex. We also saw the identity that Cosh squared x minus Shine squared x was always 1, and Thanex is always Shinex over Coshx. We also saw the logarithmic definitions for inverse Shine, inverse Cosh, and inverse Than of x. All of these can be used when solving equations. In some cases, you will need to decide which is the most appropriate one to use. Pause the slide now and try to solve each of the three equations. Some of these will use the definitions, for example, Shinex over Coshx equals Thanex. Some of them will use the exponential form, for example, Shinex equals e to the x minus e to the minus x over 2. You will need to decide which is most appropriate in each case. So for the first equation, because we have Cosh squared x but also Shinex, we're going to replace Cosh squared x with an expression involving Shinex in a similar way to how we would solve a trigonometric function of this type. So we're going to replace Cosh squared x with 1 plus Shine squared x. Notice that this is slightly different from the trigonometric case. This is because of the negative in the identity. We can now rearrange this to give us a quadratic equation in terms of Shinex. We can then solve this either by factorising or by using the quadratic formula or the quadratic solver on a calculator. These methods would lead us to Shinex equals minus 3 and Shinex equals 2. At this stage you would consider the graph of Shinex to decide whether both of these were valid. They are, because Shinex can be a positive or a negative value. We would then use the fact that x would need to be inverse Shine of 2, and then substitute x equals 2 into the formula for inverse Shine of x involving logarithms to give us x equals ln 2 plus root 5. We would do the same for Shinex equals minus 3. X is therefore inverse Shine of minus 3, so we would substitute x equals negative 3 into the formula for inverse Shine of x. This would lead us to x equals ln minus 3 plus root 10. Always double check that both of these are valid, in other words that we are not taking a negative log. For the second one, we're going to rearrange by dividing both sides by Coshx. This is so that we can use the identity that Shinex over Coshx is Thanex. We can see that the first term will become 1. So we are left with 1 plus 4 Thanex equals 0. We can now rearrange this to find Thanex. This would lead us to Thanex equals minus a quarter. Again, we would need to sketch the graph of Thanex just to make sure that Thanex could equal minus a quarter, that y could actually be that value, and it can. We would then use the logarithmic form of inverse Than of x, and we would substitute in minus a quarter in for the x values. Substituting this in and simplifying down would lead us to a half ln 3/5. You may want to work through this just to make sure you understand exactly where these values have come from. Now for the third one, we have a mixture of Coshx and Shinex. Initially, you may want to solve it in the same way as the second equation. However, the issue here is that instead of having 0 on the right-hand side, we have 3. This means that if we tried to use the same method, if we tried to divide everything by Coshx, we would end up with 3 over Coshx on this side, which is not particularly simple to deal with. So instead, we're going to use the exponential definitions for Coshx and Shinex here. We replace Coshx with e to the x plus e to the minus x over 2. Shinex with e to the x minus e to the minus x over 2. And then because it's 2 Shinex, the 2 is going to cancel with the 2 on the denominator, leaving us just with e to the x minus e to the minus x. The other side is still just 3. We can now simplify this down. We can multiply by 2 to get rid of the 2 on the denominator. And simplify this down to give us 3e to the x minus e to the minus x minus 6 equals 0. We want to turn this into a quadratic equation in terms of e to the x, so we're going to multiply through by e to the x. Multiplying through by e to the x gives us 3e to the x squared minus 6e to the x minus 1 equals 0. Here, these two terms have swapped places in the simplifying process. So we're going to solve this using a quadratic equation where a is 3, b is minus 6, and c is minus 1. You may want to write this in terms of another variable like y if you find it easier. In this case, you would solve 3y squared minus 6y minus 1 equals 0, and then replace y with e to the x afterwards. Alternatively, you may be comfortable leaving this in terms of e. If you were to solve this using the quadratic formula or the quadratic solver on the calculator, you would arrive at e to the x is either 1 plus 2 root 3 over 3 or 1 minus 2 root 3 over 3. We're going to ignore the negative solution here because 1 minus 2 root 3 over 3 is a negative, and e to the x cannot be a negative. If you consider the e to the x graph, this is not possible. Also, we can't take logs of a negative for the same reason. So ignoring the negative solution, we're going to use e to the x is 1 plus 2 root 3 over 3, and we're going to take logs of both sides. X therefore becomes ln 1 plus 2 root 3 over 3. As you can see, all three of these solutions are left in logarithmic form. Sometimes they will just say exact form rather than logarithmic form. This is what they mean when they say this. I'm now going to solve the equation Coshx equals 2. By this means find all the values of x where this would be the case. So we're going to start off by saying that x would be inverse cosh of 2. And for this, we can use the logarithmic form of inverse cosh. This would lead us to one solution, ln 2 plus root 3. Remember, however, when we first derived the definition of the inverse cosh function, we deliberately left out another value so that there was only one solution to the function. However, when we're solving an equation, we want to find all possible values. So for this, we're now going to consider the graph of y equals cosh x to see if we can now find the other solution. So considering the graph, this is y equals cosh x. Remember that it goes through 0, 1. We're going to draw a line across at y equals 2. And we can see the solution that we have found here is this one here. This is ln 2 plus root 3. Using the fact that this is a symmetrical graph, we can conclude that negative ln 2 plus root 3 must also be a solution. So therefore, whenever you're solving an equation where the solution is cosh x equals a, you must remember that there will be a positive and a negative solution because of the symmetry of the graph. If we consider the negative solution here, so the general form of a negative solution will be x equals negative ln a plus the square root of a squared minus 1, where a is the value from the original equation. We could use the laws of logarithms to take the minus up as a power. This would lead us to x equals ln 1 over a plus the square root of a squared minus 1. This is just because the power minus 1 is the reciprocal. We could simplify this by rationalising the denominator. Since we have a plus the square root of a squared minus 1 on the denominator, we could multiply the top and the bottom by a minus the square root of a squared minus 1. This is simply using conjugates. Simplifying this down leads us to ln a minus the square root of a squared minus 1. You may want to check this using the algebra just to make sure that you're convinced, but you can see that this is the value that we initially rejected when we were writing down the definition of the inverse cosh function. This is the value where we took the plus and minus, and we said we were only going to consider the positive solution here. So therefore, when we are solving equations of the form Coshx equals A, we need to either take the positive or the negative answer here, or use this formula here. These are both equivalent. Now complete exercise 5C on page 107.